Hey everybody, welcome back. This is our first set of notes here for chapter 19. This is kind of a cool chapter. We're going to talk about life's origin and early evolution. Of course, it'll come to no surprise to you that this is all going to be from an evolutionary worldview. From here on out, we're going to move from the creation of the universe and Earth all the way up through human evolution. And we're going to talk about the evolution of pretty much everything in between, bacteria, viruses, plants, that kind of stuff. So we start with nothing, we end with us, and that's going to be the story. So let's jump right into it here. When it comes to looking for life elsewhere in the universe, um, when we look at Earth species and we see that they've all got DNA, we all use enzymes, that kind of stuff. The idea is that we all evolved from a common ancestor that lived, billions of years ago. And so astrobiology is the study of basically astro is star, biology is life, so life elsewhere is the study of life's origin and distribution in the universe. So far, to our knowledge, it only exists here. We haven't found it anywhere else, but we are looking, which is fine. Um, and so what we do is we look at Earth's extreme habitats. We know that life can exist, in prairies or jungles, but we look at places that are really tough places to live, and we try to determine what's the range of conditions that we have on our planet that can support life, and then do we have similar conditions on other planets that might be able to support life. And this study in and of itself, it does have some value because we found some really cool things living in some really tough places. In the Atacama Desert, it is the driest place on Earth, and essentially nothing grows there, nothing lives there. But if you dig deep enough beneath the soil, there are bacteria that live beneath the soil. So in a place with no plants, no rain, and just sunlight, you can still get bacteria living in the dirt. We also have there's ice sheets in Antarctica, which of course never melt, and underneath of those ice sheets, we have found biofilms, which are communities of different types of bacteria all living together. So that's pretty amazing that we can have bacteria growing in a freezing cold environment, really. So when we look at all the metabolic reactions that are occurring within cells in all of the known species on the planet, including the ones in the desert and in Antarctica, they are all occurring in water-based solutions. And so what this implies to us is that life as we know it needs some form of liquid water. Um, we haven't found life existing really in a vapor or solid ice, because even solid ice will melt a little bit on the bottom. You need cells to have liquid water in them to be able to carry out reactions for enzymes to work. You need a liquid water, and so we find ourselves in a place where when you're looking at other planets, what we're looking for is water. And you guys might be aware of this. They've found some pictures of really big, kind of salty ice flows, or what appear to be, the marks of old rivers, on Mars. And of course, it's very exciting for folks who are looking for life on other planets. So Mars does have some evidence in its topography that water might have existed there a long time ago. Uh, if we are able to find any life at all on Mars, it's almost certainly going to be underground, rather deep underground, because Mars has no ozone layer. Earth has an ozone layer, and that's our atmospheric layer that has a bunch of particles of ozone, which is O3. So it's oxygen bonded to oxygen bonded to oxygen, and that's O3. It's really sloppy, I'm sorry. And ozone is really good at absorbing the energy of the solar radiation that's constantly coming to Earth, and it protects us from most of the sun's harmful UV rays. If we did not have an ozone layer, the UV radiation would be incredibly stressful to living things because our DNA would be damaged and mutated constantly when the sun was up. Our DNA still is damaged and mutated when it's exposed to sunlight, but it's at a pretty slow rate. If you remove that ozone layer, we would be in a world of hurt. And so our thought is, if there are some bacteria that are able to get some sort of a little bit of water, they're going to have to be in the dirt because they can't be on the surface. The ozone, or the lack of ozone rather, the UV radiation, would probably destroy them. It would destroy their DNA or RNA or whatever they're growing with up there. So let's talk about how this all got started. Um, the most popular theory, uh, naturalistic theory for the creation of everything that ever was, is the Big Bang Theory. And the Big Bang Theory is the idea that the universe began in a single instant or a single moment, 13 to 15 billion with a B years ago, a long time ago, 13 to 15 billion years ago. The idea that all the matter that exists today, all of the matter and all of the energy, suddenly appeared. It had, I think, condensed down to a teeny tiny, infinitely dense point, and it basically exploded out from that single point. I've heard some people say it shouldn't be called a Big Bang, but a big expansion. They don't know if it was so much of an explosion, but rather a swelling or expanding of all the matter that was. If you're a young Christian student, you might think this is not such an odd thing for all matter to suddenly appear that exists in the universe and to explode outward from a single point, because you are likely taught that God spoke the universe into existence, and perhaps that's exactly what that would look like. All matter and energy suddenly appearing. At any rate, the dates certainly wouldn't match up between those two views. Um, so once all of the matter of everything that ever was expands out, you get some simple elements like hydrogen and helium are going to form really right away. Hydrogen is not that terribly complicated. If a positively charged proton becomes attracted to a negatively charged electron in this flying space dust of the future of everything, and the electron and proton get together, you made a hydrogen. It's just that easy. Uh, Helium, two protons, and you've made a helium. So you can get these things to form right away, and that hydrogen and the helium are also the main building blocks of our sun. And so once you have hydrogen and helium in a very dense area together, you do have the potential to create a little bit of power through nuclear fusion, and then you can start powering a sun. The idea is that as these gases were thrown throughout the universe, gravity is the force that attracts any two bodies with mass in the universe to one another. Gravity is dependent upon the mass of the two bodies. That's m1 and m2. And it is also dependent upon the distance between the two bodies. And then there's this big constant in front of it as well. But that's okay. It's not physics. You don't have to calculate it. I just want you to understand it so you kind of get how this works. And so I am much heavier than, a fifth grader. And so the Earth's gravitational pull on me is actually a stronger pull than it is on a fifth grader who's like weighs half as much as me or less. So that's the idea with gravity, is that some pockets of gases might have been heavier than others, and they would actually draw neighboring gases to them and condense. And if hydrogen and helium are in there in enough quantity, we can start to make a star. And so that's the idea. Once we have a star, the star is very dense, and it has a very large mass. Then the other little particles of whatever that have been tossed out can likely start to orbit that very massive star. If the pull is not strong enough to just suck them into the star, they can orbit that star. And then in the course of their orbit, they can collide with other little asteroids and particles and become more massive. And as they are more massive, they will draw their neighbors to them, and so on, and so on, and so on. So, Early stars would likely have scattered some of our heavier elements. Those elements could eventually get together to form asteroids, and those asteroids could hit other asteroids and hit other asteroids and make small planets, and eventually we get galaxies. Asteroids near our sun would collide, merge, and gather more material because as they've collided and become more massive, they exert a stronger gravitational pull on their neighbors. And the idea is that this gradual buildup of materials and asteroids and that kind of stuff is what formed Earth and the other planets that are in our solar system. So that's the idea. And so early Earth is basically just a big rock that's just kind of cruising around this early sun, and it's going to be hit by meteorites all the time because we don't have a protective atmosphere or anything to keep us safe. So these meteorites are just going to be hitting Earth constantly, and those meteorites are going to bring additional elements, um, which can provide the components for land, sea, and atmosphere. And it's a rather popular idea that the water that exists on Earth probably did come from meteorites. Um, when I think about how much water is in the ocean, I personally struggle with this idea a little tiny bit, uh, but that's just me. You might not. So that's where we got our water and our land and our atmosphere and our ozone and everything from. It all came from meteorites, I guess. I don't know. Do with that what you will. The inside of the Earth being very hot would give us volcanic eruptions, and of course that would add additional elements for land, like we see even today. Earth started out with really, we think, little or no free oxygen at all. We mentioned a couple chapters ago that uh, there were rock bands of iron that had not oxidized. The iron was black as opposed to, red or orange. And so the idea is that if these metals are not oxidized, there must not have been oxygen in Earth's early days. And then as oxygen came about later, then the iron started to oxidize and we started to get these red and orange bands in our rock layers, and we can kind of use that as a clock. The deeper rocks have no iron oxide. The more shallow rocks have iron oxide as an indicator of when oxygen came onto the scene. All of our water was in the form of a vapor to start with. There was no liquid water, but over time the earth would cool and that liquid water could form in little pools on Earth's surface. And then we have a variety of elements from meteorites and volcanoes, and we have liquid water pooling on the surface. And that is really going to be our stage that we are setting for a now lifeless Earth that we are hoping to get life on. So we're going to stop there at 19.3. This is going to be how we think life might have began, I guess. Uh, and we'll stop with the point where we are right now, where we have Earth and we have water. So that's it. That's a good place to stop. Thank you for your time.